Introducing Remarkable Paper Pro, the ultimate paper tablet. With an all-new Canvas.
This college algebra course is different than other college algebra.
Typical. Okay, very good, very good. That ends the first chapter. So I'll let you go, and excuse me, it ends the first section. So I'll let you go, and I'll see you next time with the second section, vectors and space. Very good. Okay, bye-bye. Hello, hi, hello. Ready for the second section of the first chapter. So because this is the second section, we are going to introduce something new. Which is a look back on the previous material, which we didn't have anything to look back on in the first section. So here I have a couple of quick questions that will give a person a chance to feel like they're sure that they're following the main thrust of what we're talking about. So this is an easy one. They're all supposed to be relatively easy, but they're supposed to be just a kind of a quick check-in. All right, so there's 4 linear systems, 1, 2, 3, 4. They're all in echelon form, so a person doesn't have to do the arithmetic. And it simply says how many solutions does each one have. So for the first one, what do you think? So there is no solution here because 0 equals minus 1. Anytime there's a contradictory equation, you stop and say no solution. Over here, second one. So this is the one a person could be fooled by the 0 equals 0. That 0 equals 0 does not signal that there are infinitely many solutions. That's not right. Instead, what's happening here is that there is a row led by z, there's a row led by y, there's a row led by x, and there's no contradictory row. So we're looking here, in this case, we're looking at unique solution. Down here. So here, again, there's a 0 equals 0, but again, we're not going to be confused. There is a row led by x and there's a row led by y, but there's no row led by z. So we're looking at infinitely many solutions in this case. And finally down to here, this fourth one. And so I'm sure that at this point you've seen that there's a contradictory row, and so never mind the 0 equals 0, never mind that there's no row led by z. No, all that doesn't matter. It's a contradictory row. So the answer is no solutions. Okay, so that was the first. Let's see if I can manipulate my stuff here. There we go. There we go. And here's the second. It just says produce a 3 equations, 3 unknown system that has infinitely many solutions. Produce one with no solutions, and then also produce one with one solution. So I gotta produce that on a piece of paper here if I can figure out how to do this. There we go. Produce that on a piece of paper. So I'm just going to make one up. Of course, you would make up a different one. The idea with these systems is, of course, so I gotta produce that on a piece of paper here if I can figure out how to do this. There we go. Produce that on a piece of paper. So I'm just going to make one up. Of course, you would make up a different one. The idea with these systems is to produce, for example, infinitely many solutions. You might produce an equation that is redundant on the other two, that is just a repeat of the other two. So let's have a look here. Let's see. How about something like x plus y plus z equals 1. 2x minus y equals 5. And then I'll just make the third row be a repeat of the other two, the information in the other two somehow. So for example, how about if I take 2 times the first row and add it to the second row? So 2 times x plus 2x makes 4x. 2 times y minus y makes plus y. 2 times z plus 0 makes 2z. 2 times 1 plus 5 makes 7. And that's going to be infinitely many solutions. Okay, now if you want to have no solutions, then you want something like this. You want to do basically the same thing. X plus y plus z equals 1. 2x minus y equals 5, just a couple of equations that I made up. And then over here I'm going to do 4x plus y plus 2z, and then I'll put anything but 7 here. So as long as I don't take twice the first row and add the second row, if I do something other than 7 here, I will get a contradiction, because the left side is twice the first row plus the second row, the right side is not. So if I put anything but 7 there, how about minus 5? No solutions. So it's about linear combinations. That's what it's about. And last, for unique solution, really the thing about unique solution is that it's what almost always happens unless you've got some very special circumstance. So I'm just going to do here, how about the same first two rows? X plus y plus z equals 1. 2x minus y equals 5. And 4x plus y plus z, not 2z, just plus z. So something different here. The third row is not twice the first row plus the second. And I can write anything I like over here. 94. Okay, and there'd be unique solution. Okay, so the three things that can happen is there can be redundant, there can be a contradictory, or that can just be really kind of the random case of just any old jumble of things. Whoops. Come on, there we go. Okay. Okay, so that's what can happen in those three cases. All right, so let's bring up the material for the day. Come on, there we go. For some reason, the clicker is giving me trouble. Okay, so I want to look at, last time we had solutions sets that had a particular form. It was a particular vector plus the vectors that made up the solution set of a homogeneous system, the associated homogeneous system. So that had a particular form, and last time I was a little bit, you can only do so many things at once. So I started off by introducing matrices and vectors and saying that they are, for the purposes of last class, they just were holding numbers. That's all. They were just like a little database that held numbers. Well, now I want to introduce, it's really, I expect it to be a review. I want to introduce the geometry that vectors and matrices, but really vectors at the moment, represent. So the the thing is that there is, behind linear systems, there is a geometry. It all makes sense if you think about it geometrically. So you have to start somewhere. We started by solving them. That makes sense. But when you step back a little bit and look at what they're about, that makes a lot of sense too. So here, for example, are two equations, two unknown systems, 1, 2, 3 of them. This two equations, two unknown systems is a unique solution. You can see that the second equation is not a combination, somehow not 5 times the first or anything like that. This one here has no solutions. You can see that the second equation on the left-hand side is indeed just the first equation, somehow not known system, 3 of those. If you think the thing is represent. So the thing is that there is, behind linear systems, there is a geometry. It all makes sense if you think about it geometrically. So you have to start somewhere. We start started by solving them. That makes sense. But when you step back a little bit and look at what they're about, that makes a lot of sense too. So here, for example, are two equations, two unknown systems, 1, 2, 3 of them. This two equations, two unknown systems is a unique solution. You can see that the second equation is not a combination, somehow not 5 times the first or anything like that. This one here has no solutions. You can see that the second equation on the left-hand side is indeed just the first equation repeated, but on the right-hand side it isn't. So there's a contradiction there. No solutions. And over here you get infinitely many solutions because the second equation is really just double the first equation. It's a repeat. And when you think about the geometry, that's the 3 things that lines can do. When you plot these 3x plus 2y equals 7 and x minus y equals minus 1, when you plot them as lines, if they fall kind of askew here, or if they fall parallel here, or if they happen to be the same line, why then you get the three cases that can happen. So the fact that in linear systems three things can happen in these three pictures, it all makes sense now. You say, well, that's exactly what geometrically can happen, and that's indeed one of the advantages of the geometry, is that it makes clear to a person just exactly what could conceivably be going on. The geometry is a way to understand what linear systems have to say, and we'll be looking for as many different ways to understand what systems have to say as we can grab our hands on. Okay, so I want to talk then about the geometry. So to talk about the geometry of this general solution sets that we talked about last time, I have to start by talking about vectors. What are vectors? And again, I anticipate that this is, for most folks, this is a review, that you've seen this before either in a prior math class, so let's say Calculus 3, for example, or maybe in a physics class, for example. Okay, so for our purposes, a vector geometrically will be an object consisting of a magnitude and a direction, and the right way to think of it is that it models the displacement. In this case, for in a Calculus 3, for example, or maybe in a physics class, for example. Okay, so for our purposes, a vector geometrically will be an object consisting of a magnitude and a direction, and the right way to think of it is that it models the displacement. In this case, for example, you might be going to the left by 1 and down by one. And that's a displacement, and I've drawn that displacement as an arrow. The arrowhead, of course, points to where you end, and the beginning of the arrow points to where you started. Vectors, that is to say, for example, displacements, with the same magnitude in the same direction are equal. So I have a bunch of vectors drawn there on the plane, and they all have the same magnitude, they all have the same direction. They are the same vector. I know that they look like they're different vectors because they're drawn in different places, but they're all the same displacement. So they're all the same vector. Each of them is a 1 over and 2 up displacement. Okay, so if I want to write down what is the displacement, then I need to write down the start point and the end point, and then do the subtraction, b1 minus A1 is the difference in the x direction. B2 minus A2 is the difference in the y direction. So for example, a 1 over in the x direction point and the end point. If I want to write down what is the displacement, then I need to write down the start point and the end point, and then do. If I want to write down what is the displacement, then I need to write down the start point. And the end point, and then do the subtraction. B1 minus A1 is the difference in the x direction. B2 minus A2 is the difference in the y direction. So for example, a 1 over 2 up vector is written as 1, 2. And we often picture a vector by starting at the origin, just because you got to start somewhere, so it's convenient to start at the origin. If you start at the origin, then the vector whose components are v1 and v2, for example 1 and 2, will end at x equals 1, y equals 2, or end at v1, x equals v1, and y equals v2. So we often say that the plane is the set of points x1 comma x2, or the plane is the set of vectors x1, x2. And we won't really distinguish all that much. We'll find it convenient sometimes to blur the distinction between the point and the vector which when started at the origin ends at that point. And all this stuff, one advantage of all this stuff is that it all instantly extends to higher dimensions. So 3-dimensional, 4-dimensional, 5-dimensional, and sometimes when you work with linear systems, you're working with hundreds of unknowns, hundreds of equations. So you could have hundreds of dimensions in your vector, in your collection of vectors, and so all this stuff extends immediately to many dimensions. Okay. The operations that we introduced for vectors last time were addition and multiplication. Multiplication is the easier of the two, so starting with multiplication. If you multiply a vector times 3, you make it 3 times as long. Pointing in the same direction, but 3 times as long. 3, you make it 3 times as long. So starting with vectors last time were addition and multiplication. Multiplication is the easier of the two, so starting with multiplication. If you multiply a vector times 3, you make it 3 times as long. Pointing in the same direction. But 3 times as long. If you multiply a vector by -1, you make it point in the other direction. If you multiplied a vector by -3, you'd make it point in the other direction and be 3 times as long as it was before. So scalars, the 3 or the -1 here, rescale the vector. The geometry is they simply make it bigger or smaller. That's all. The addition of two vectors, again, familiar. I expect that this is a review for most folks. The addition of two vectors is if you add v and w, then the way to construct the sum, v plus w, is you take the end point of v and the begin point of w, put the begin point of w on top of the end point of v, and then the vector v plus w extends from the beginning of v to the end of w. Again, we're thinking of vectors as being a displacement. So one way to imagine what's happening here is imagine that you're on a boat, and over the course of a minute the boat moves this way. Is a vectors as stand point of w on top of the geometry is they simply make it bigger or smaller. That's all. The addition of two vectors, again, familiar. I expect that this is a review for most folks. The addition of two vectors is if you add v and w, then the way to construct the sum, v plus w, is you take the end point of v and the begin point of w, put the begin point of w on top of v, and the way to construct the sum, v plus w, is to add v and w, then addition of two vectors. Addition of two vectors, again, familiar. I expect that this is a review for most folks. The addition of two vectors is if you add v and w, then the way to construct the sum, v plus w, is you take the end point of v and the begin point of w, put the begin point of w on top of the end point of v, and then the vector v plus w extends from the beginning of v to the end of w. Again, we're thinking of vectors as being a displacement. So one way to imagine what's happening here is imagine that you're on a boat, and over the course of a minute the boat moves this way, and you on the boat on top of the deck move this way. Then combined, your motion, the boat underneath you and you on the deck of the boat, your combined motion is this. You often hear this described as the parallelogram rule because, see, you draw a parallelogram and then the v plus w extends from the lower corner to the upper corner. So it's got a kind of a nice picture. I want to talk about some of the usual geometry things that we're going to use throughout the course of the course. So, for example, a line. So we're going to use throughout the course of the course. So, for example, a line. So we're used to maybe y equals mx plus b expression of a line, but we have a reason to think here about the vector expression of a line. This is the line that goes through 1, 2, and 3, 1. There it is in dark. 1, 2, and 3, 1. And you'll see that it is in dark, 1, 2, and 3, 1. And you'll see that I've written that as 1, 2 plus t times 2 minus 1. So the 1, 2, of course, comes from the 1, 2, and there's the vector 1, 2. Where's the 2 minus 1 come from? So you take 3 minus 1, and 1 minus 2. Again, 3 minus 1 and 1 minus 2. In other words, you take the offset, so the slope. Take the offset and you get 2 and minus 1. So there's the 2 minus 1. That tells you how to get from the 1, 2 vector to the 3, 1 vector is the 2 minus 1 vector. Okay, and then of course this line, the dark line, is comprised of the endpoints of vectors that have this form for various t's. T equals 1, t equals 2, t equals 0, t equals minus 1, t equals minus 2. Okay? Of the endpoints of vectors that have this form for various t's. T equals 1, t equals 2, t equals 0, t equals minus 1, t equals minus 2. Okay? All that stuff is, I hope, familiar from previous classes. We often call that the direction vector for a line, 2 minus.
That is, it is comprised of the endpoints of those vectors. The vector associated with the parameter t.
Minus 1 is the direction vector for a line, and in higher dimension you just have, instead of having 2 components, you might have 3 components, 4 components, 5 components, kind of stuff. Planes. So planes work basically the the same way, and you'll recognize that this has a familiar form. It has the form of the solution set of a linear system, and that's why we're talking about all this stuff. Here's a plane drawn there in that kind of funny color, the yellowish color. So 1, 0, 5, 2, 1, minus 3, and minus 2, 4.5. So kind of just a generic plane, random plane, nothing special about it. And it consists of the endpoints of vectors in this set. You recognize the 1, 0, 5. That's actually this greenish vector here. So you recognize the 1, 0, 5. Where did the 1, 1, minus 8 come from? Where did the minus 3, 4, minus 4.5 come from? Well, it came from the same place that the vectors came on the previous slide. So where for example, did the 1, 1, 8 come from? It's 2 minus 1. One minus 0, minus 3, take away 5. Where did the minus 3, 4, minus 4.5 come from? It's minus 2, take away 1, 4, take away 0, 0.5, take away 5. And that's the two red vectors that you see here. Those red vectors are drawn in the plane. This is the vector representing displacement, and this is the vector representing displacement. Okay, so the vector associated with t and the vector associated with s, displacement, and this is the vector representing displacement. Okay, so the vector associated with t and the vector associated with s are drawn as red. They lie in the plane. Their body lies in the plane, not just the tip. The 1, 0, 5 vector, only its tip lies in this drawing. Only its tip touches the plane. It starts at the origin. And then those column vectors come from those places. A set of that form, a form that we at this point recognize as the solution set of a linear system. A set of that form is called a k-dimensional linear surface. This is, of course, going to be a two-dimensional linear surface because a plane is flat, so 2 dimensions. A k-dimensional linear surface, sometimes called a k-flat. Okay, so this, of course, takes us back to what we talked about last time, that we are talking about the solution sets of linear systems, and we can see them as having some sensible geometry. The subject is called linear algebra because everything is linear. Lines, planes, that kind of stuff. Okay. Okay, next time we're going to talk about length and angle measures. So we'll see you then next time. If I can work my systems here, we'll see you then next time. There we go. Okay. All right. Bye-bye. Hello, 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 hello. Welcome back. We're going to talk today about length and angle measure. But first, I want to do another quick example of some look-back questions. Some questions about the previous section that will, I hope, give a person some sense of whether they know what's going on. So for starters here, we have these three. So the first one is, what is a linear equation? So if you have an x plus 2y plus 3 z equals 4, or minus x plus 2y minus z equals 1, what does that represent geometrically? So, of course, in doing the homework, and because the materials review probably from previous classes, you recognize that x plus 2y plus 3z equals 4 is, strictly speaking, is a one-equation linear system. One-equation linear system with two free variables, y and z. So you can express x in terms of y and z. It's not very. So you can express x in terms of y and z. One equation linear system with two free variables, y and z. So you can express x in terms of y and z. It's not very hard. You can express x in terms of y and z, and so you get a solution set that looks like particular vector plus y times a vector plus z times a vector. So again, x plus 2y plus 3z equals 4, or the other one, is a linear system with one equation. So we know what the solution set looks like, and the solution set looks like the equation that we saw last time for a plane. So x plus 2y plus 3z equals 4 is some kind of plane in 3 space. It's a two-dimensional flat surface in 3 space. And likewise, minus x plus 2y minus z equals 1 is also a flat two-dimensional surface inside of 3 space. Okay. So that's why we're interested in, that's why we call the course linear algebra, because it's about these linear things. What are the possibilities, question 2, what are the possibilities for the intersection of two planes? So really the point of this question is to have a person think about, in your head, you imagine two planes. Some people are better at imagining these kind of things than others, but still, two planes, it's like two pieces of paper. If you lay two pieces of paper out in space, what can happen to those two pieces of paper? Well, it seems to me there's a limited number of cases. If you have two planes, it can be the case that the two planes are parallel. That could happen. It only happens in a special case, but nonetheless, it could happen that the two planes are parallel and never touch. The other possibility is that it can be that the two planes are canted at some kind of angle to each other, and so in fact the two planes touch, and when they touch, they meet in a line. It's not possible for two planes to intersect in exactly 2 points. It's not possible for two planes to intersect in exactly 1 point. If two planes intersect, they have to intersect either in 0 points, meaning that they're parallel planes, or else in a line, in infinitely many points. And then, of course, question 3 is the 3 planes. What can happen? So if we have 3 planes, which we're linking in our mind with 3 linear equations, if we have 3 planes, what can happen? Why, it can be the case that 2 or maybe all 3 of them are parallel to each other. That can happen. So there is, in fact, no common intersection to the 3 planes. That could happen. A more likely case, though, is that the 3 planes intersect in the following way, that 2 of the planes intersect in a line, and then the 3rd plane cuts that line, so that you find 1 point, a single unique point, a common point for the 3 planes to intersect. And then the last thing that can happen, and again it probably strikes a person as unlikely, but doesn't mean you couldn't make up an example of it, is the first 2 planes intersect in the line that we just had a second ago, and the 3rd plane also happens to share that line, so all 3 planes intersect in that line. So the two cases, the cases of where the three planes are parallel, might strike you as being not very typical, as being a little bit unusual, a little bit off the beaten path. You said, well, you'd have to set the system up very specially in order to have that happen. Yeah, that's probably true. And likewise, to have the three planes intersect in a single line, you say, well, that if you're just going to throw three planes into space, you wouldn't think that would happen. Yes, very true. And then the third case, that the three planes intersect in a single point, two of the planes intersect at a line, and then the third plane cuts the line. That's kind of, you say to yourself, that's kind of the case that I kind of expect to happen most of the time. Yeah, that's right. We've used the word non-singular before. But anyway, that's kind of the random case that you think would happen most often. Okay, all right, so let me go to today's material on length and angle measure. And again, I'm anticipating that the that the material for today is largely a review, that you probably had it before in some other math class like Calculus 3, or else you might have had it in say a physics class or some other class like that. And so we're we're going to go through it a little bit more quickly than we go through material that we thought was entirely new to everybody. Okay, so the length of a vector. Length of a vector is the Pythagorean length. You take you square each of the components, and then you take the square root. You square each of the components, sum them up, and take the square root. We use absolute value bars for length here, just because absolute value bars are the general symbol that you use in mathematics to indicate magnitude or size of, and so that makes sense for length of a vector. And just as an example, the length of -1, -2, -3 works out to be 14. Notice that the negative signs do not matter. You don't run into trouble with length when the vector points in the negative direction or any such thing. That squares make the negatives go away. So the length of this particular vector is the square root of 14, which is not a very particularly handy number. It will often be the case that we want to take vectors that are of kind of an arbitrary length, like square root of 14, and resize them to make them be of length 1. So we'll take this vector and come up with a new vector that has length 1 for a size. And the right way to do that, that's called normalizing the length. The right way to do that is to divide the vector by its size. In this case, I will multiply v by 1 over the square root of 14. Multiply v by 1 over the square root of 14. See the length of v on the bottom of that fraction, and we end up with a square root of 14 on the bottom of each of those three fractions. And when you do the calculation, -1 over the square root of 14 quantity squared, -2 over the square root of 14 quantity squared, -3 over the square root of 14 quantity squared, and you add them all up and take the square root, you end up with 1, which is what I wanted. So normalizing is how you turn a vector and start with a vector and get a new one whose length is 1. And it works as long as the original vector is not the 0 vector. Of course, if you tried to divide the 0 vector by its own length, you'd find yourself somewhere where you don't want to be. Okay, I want to introduce an operation. Again, I'm anticipating that this is review for folks, so introduce in some, in not really telling the truth sense. This operation is called the dot product. Sometimes inner product, sometimes called scalar product. Authors call them different things in this context of two n-component real vectors that have to have the same number of components. Dot product of two n-component real vectors is you take their components, first components, second components, third components, you multiply the components, multiply together the first components, multiply together the second components, etc., down to multiplying together the nth components, and then you add the result. In this book, I'm writing it with kind of a bold-faced dot. That's just just a convention that I've adopted. You can't write a bold-faced dot on the whiteboard, so there's only so much a person can do there. But I do think that making the dot especially dark helps a person to remember that it's not regular multiplication, not scalar multiplication. It is instead some different operation. A person could tell, of course, because they're vectors, that it isn't scalar multiplication. But anyway, I've adopted this kind of darker dot that you won't necessarily see in other books. And it's not hard here to do the operation. 1 times 3, 1 times minus 3, minus 1 times 4, add them all up. Turns out it adds to minus 4 in this case. And the thing to notice about the result is that when you take two vectors and combine them in this way, you don't get a vector, you get a scalar, which is why it's often called scalar product. And the thing to notice about the result is that when you take two vectors and combine them in this way, you don't get a vector, you get a scalar, which is why it's often called scalar product. Okay, and then the other thing to notice with the dot product is that if you take the dot product of a vector with itself, you get the vector's length. The importance of dot product is that it tells us something about the spaces that we're interested in, about the linear spaces that we're interested in, and this result really gives you the central core of the idea here, is that if you have two vectors, u and v, in
Collinear.
Collinear. Collinear.
real n space, so you have available the dot product, then the length of u plus v is less than equal to the length of u plus the length of v. And this picture really tells you what you want to know here. The length of u plus v, so that's the length of u plus v right there, that's the darker of the two vectors, is less than or equal to the length of u plus the length of v. And of course that person recognizes it because it's written on the slide, that the shortest distance between 2 points is in a straight line. So that's called the triangle inequality for the obvious reason, because you illustrate it by drawing a triangle, but it says something about how spaces work. It says that spaces are flat in some sense. The proof of the triangle inequality, you can find all kinds of proof of them all over the internet. For example, if you Google, but I chose a particular one that I want to illustrate something. So because all of the numbers are positive, I can square both sides here, and I don't have to worry about changing the direction of the inequality. So I took the length of u plus v and squared it, and I took the length of u plus the length of v and I squared it. And from the previous slide, I remember that the length of a vector, the length of u plus v in this case, the length of a vector squared is equal to the vector dotted with itself. And here, when you square a plus b, you get a squared plus 2ab plus b squared, and so I just multiply that out. And then you go on and do some algebra. It turns out, we haven't given it as a lemma, but it's one of the exercises. It turns out that you can distribute the dot over the plus sign here and get u dot v, excuse me, u dot u and u dot v, and v dot u and v dot v. And likewise here, length u quantity squared is u dot u, length v quantity squared is v dot v. You see that the u dot u and the u dot u cancel. You see that the v dot v, oops, there it is, the v dot v and the v dot v cancel. And when all the smoke clears, we've got 2 times u dot v, the u dot v and the